All right. So not sure how many of you have ate your dinner. If you haven't, well, you know, I sometimes I feel like there are pros and cons during the pandemic. So the good thing about the pandemic is that, for now, like because we are not in the same classroom, so you can feel 100% comfortable about just like grabbing your dinner, or if you are in Asia, you can probably grab your brunch or something else, and like sit in front of your monitor and just watch the lecture without worry about like other people without worry about other people like smelling your food, right? And another thing that so that's one thing I feel good about it. And for so another thing which I don't know if you noticed regarding the before the class is that we were playing some songs before the lecture, and some of the songs that we played was about it's called Bike Cry, and not sure how many of you ever heard about this song or ever pay attention to the music when you are installing a software. So this is actually the same song of Mac OS 10.4 Tiger. And that was so if you pay attention to the lyrics, they are actually there are some flavors of engineering inside there. So it's a very interesting song, and I do encourage you to spend time like go through it again. Okay, so Rogelio, what's your you raised your hand. Do you have any question?
Hi, yes. Are there any slides for today?
There are slides for today. Why are you asking this?
Is this the intro slides?
What?
Is this the set of intro slides? Because I don't see them on the class website. Maybe I'm just
the class website does have the slides for today if you check the preview session. Okay, so regarding the slides, we have two types of slides. One is the pre-release slides, and the other is the after-release slides. And the pre-release slides won't include the class discussion. And if you really want a slide, you can go to the class website. There will be a pre-release slides for you to download for the lecture today, and you should be able to see it. And I believe it's already in the
yes.
Yeah. All right.
Thank you.
All right. All right, so now I think we are good at going into the context for today. So before we start, it's always a good idea to remind you guys, where are we coming from? So if you were in my class last quarter, you must remember this guy, and I'm not sure what's your feeling about him right now. Maybe hate him, or maybe you love him, but he's John von Neumann, and he is really influential in terms of a computer system or overall the computer science. And I'm a little bit surprised that we didn't give him the same degree of respect as what we have been given to giving to Turing. But well, von Neumann is really important in a way that he defines the modern computer architecture in a way that he said that the modern computers should have a processor, should have a memory, should have the storage, and the persistent storage help us to to store your program instructions and your user data persistently. And then by loading different programs into your memory, your processor will fetch those instruction processed on different sets of data in a way that your computer can perform completely different functions without physically reconfiguring it. So if you are thinking about, like, you know, why we have the software industry, it's just because of von Neumann's contribution. And it's not, so the Turing just defined like how you should write a program, but what really make writing program, this thing becomes easy and possible is because of the von Neumann architecture. So the von Neumann architecture is actually very, very important to the success of modern computer industry. And in von Neumann architecture, the processor is queued program in this way, in a way that your processor contains a program counter called PC, tells where the upcoming instruction is in the memory. So the processor reads the PC, when a clock signal comes, the processor reads the PC, and the PC tells the processor where in the memory should I fetch the instruction. And then I read over this instruction and see what instruction want me to do, perform the corresponding operations, and then that's how the rest of the story happens, right? So this is von Neumann architecture, and without von Neumann architecture, it's impossible to have a software industry like this. However, another aspect of von Neumann architecture is that the von Neumann architecture only defines hardware, and without an intermediate kind of software in between the programs that you want to execute on the hardware, it turns out that this is what would happen, is that everyone, because there is nothing helping us to manipulate the execution of all the user programs. So it turns out that everyone has to line up in front of a computer to fight for the slots of executing your computation, right? So that's not great. So that's why we start to have the operating system. So today we are going to talk about the idea of So today we are going to talk about why we need the operating system. So the idea of operating system is like this. So you have a set of user program, and without the operating system, your program will directly execute on this computers. And however, who comes first? And is there possibility of concurrent execution? The answer is no, because only one can use at that time, right? So that's not great. So that's why we have we have an operating system which provide an abstraction. So everyone interact with this abstraction called operating system, and the operating system would help us to receive this program, this request, and try to schedule them, try to manipulate how to share them. So it turns out the evolution of operating system nowadays is that we will support this function. So first of all, as we said, the operating system present an illusion that you only need to interact with me. You don't have to interact with the rest. So it's a virtualization. And then a lot of people can just throw things to the operating system without worrying about like if my program will be run or not. So it supports concurrency as well. And even though I have multiple programs or the same program with multiple threads, they can run concurrently. And the last thing is that your data can be persistently stored in your system, and that's all supported by the operating system. And starting from today, we will talk about the first part of the topic, which is virtualization. So regarding virtualization, today we are going to show you the evidence how the operating system virtualize your computers, and then what's the basic abstraction the operating system provide in virtualizing your computers, and then to support this virtualization better, what kind of architectural support and the operating system modes that we have in a system. So these are the three topics that we are going to talk about today. So now, first of all, we are going to talk about virtualizing your computers. So as we said, a computer von Neumann computer has processor, has memory, has persistent storage. You have a set of programs running on top of that. And the goal of the operating system is that the software is not aware about all the underlying hardware. You only need to know that, okay, right now I'm interacting with Linux, Mac OS, or Windows, iOS, or Android. That's it. And the rest of the stuff, all the services regarding the hardware is provided by the operating system. And I just use the system facilities supported by the operating system without worrying about what hardware is. So the basic idea of operating system is like this, right? So it's providing a vehicle of virtualization. So what does that mean by virtualization is that so right now I only highlight the word, right? So you have a program called Word. The Word is not aware about like how much physical memory you install, how fast your processor is, how big the storage you have. And it only sees, well, I have a processor, I have a set of memory, and I have a set of IO devices that I can use. And those are the features provided by the operating system. So the Word itself only see the highlights part that, well, I have a processor, I have memory, I have IO, and that's all what I can use. So that's the idea of virtualization provided by the operating system. So, for you to use this facilities, like if you request any service from your processor or memory or IO, you have to go through an API, application interface, also provided by your operating system. So here is the idea of an operating system. We provide some kind of API, and the application only uses API to interact with those virtualized hardware components we provide in the operating system in a way that your software doesn't have to know what exact processor, what exact memory module, what the exact memory locations in the physical chip, and what exact location or what exact command I need to interact with the SSD. They cover all these low-level details by as long as you know you use the API provided by the operating system. So that's the whole idea of an operating system, is that we provide a set of API for you to interact with the computer. And in this way, each operating system just provides an illusion of a virtual machine for each running program. And the running program, later on you will know, it's called, the running program in the operating system, we call this running program as a process. And the operating system is also helping us to maintain the architectural states of a von Neumann machine that executes the running program. And each virtualized environment provides architectural facilities through some sort of application programming interface or the API, and dynamically manipulate the usage of this virtualized resources into physical resources. So that's the whole idea of operating systems. So to give you a feeling about how your operating system virtualizes your hardware, here is the C code that I wrote. So in this C code, the first line, I declared a global variable called double A. So it's a double precision number, a variable called A, and it's global variable. And by global variable, it means it's visible by the rest of the program, and it's also statically allocated in your program code. And well, then go through the first line. You know, there are some declarations about variable CPU status I, and there's a pointer address from malloc. And then I declare another variable called CPU set T. You will know why am I using this. And then I have I initialize this CPU set variable. It's actually a mask to initialize all of them to 0. So now it's a 0 mask. And then I set the mask to be 4, meaning that I want to make a mask that would later on help me to select the 4th processor. By processor, it's the processor cores that I have in a system. And then I call a function called schedule set affinity, which fix my current running program into that processor. So assuming that I have, no matter how many processors I have, right now I just fixed my program into that processor. And then some argument checking, and I create a random number assigned to A. And then first I print the value of A, and then as well as the address of A, right? And now later on, I sleep for another a few seconds later, and I print the value of A and the address of A again after sleep. So this is a simple program, right? But let's see, what if I execute multiple instances of the program, and what would happen? So now let me show you in this directory, I have exactly the same program that I have here for you. And now to make sure that I'm not cheating, see, currently there's no binary files there. So I just compile it with C programs right now, and with C compilers right now. So you know there is a virtualization a binary that's just just generated. And in the meantime, I'm later on I'm going to run a script. The script contains commands like this. So if you are not familiar with Unix, then this series of command means that I'm going to launch virtualization with the argument A, and then using an ampersand to put it in the background. So this one actually means that I'm going to execute 4 instances of the virtualization program in the meantime, and each one with different names. So now let me run this script for you, and let's see what would happen. So now I'm running these 4 instances together, right? So from this from this demo, you will see, first of all, everyone has the same memory address for variable A. So everyone had exactly the same memory address for A. And although I launch process virtualization A first, but actually because of the operating system scheduling, process B gets to run first. And the process B is using CPU 4 at this time. And it generates the value of this to A. And now process A running on CPU 4, it generates another value of A, and both of them have the same memory addresses, right? So, and later on, process B, after sleep, it wakes up again, and it still has the same value of A that was previously generated, even though A, B, C, D, they have been executed, they all have the same memory addresses. So that's what's happening here, right? So you will see that, well, wait a moment. Everyone has the same address, right? But how come the value is not modified at all, right? How come everyone can preserve the same value? How come everyone can run on the same processor, right? So here, that's the evidence of what virtualization in operating system has been done for you, right? So let's look at this, right? So if you look at the demo again, right, that's exactly the code that we have been running for you. And this is another run of the program. And as you can see, well, the same processor, the same memory address, different values, but they are all preserved, right? So that's an evidence of virtualization. By so for now, we can see that virtualization helps us to achieve one thing. So processors can use the same processor. Processes can use the same processor. All the running instances, they can have the same processor, and they are not affected by they all can preserve their values, and they, even though they have the same address for variables. So so in some ways, right, the processor is pretending that I'm serving each process exclusively. And the memory address is also pretending that even though I have the same address, but I'm also exclusive to anyone. So that's the virtualization, right? So now I want you to think about why we have this virtualization and what's the good thing about virtualization, and put your answers through the Zoom poll feature for and think about it within 90 seconds. Okay, now let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now we have finished the first round. That's the individual voting and thinking process. So I believe everyone should have some idea in your mind. But right now we are going to practice the peer instruction a little bit. If you haven't been to my class before, we are going to the second round, which is the group discussion, which I will break you guys into two different groups, and then you will discuss in the small room with your friends and or people you know. And some of you later on in a group as the scriber should tell us like, okay, what's your thoughts about the answer by well, it's because we have two teams, so I'm not going to use a random number generator this time. But as long as your group feel like I want to share my thoughts, then just raise your hand, and at the end we will count how many groups give us the most insight, and well, which group give us the most insight, and every one of you in a group will get like $5 gift cards. So now because the limitation of Zoom, there's no way you can view the slides after we enter the breakout room. So I already sent out the screenshot of the question that you just discussed through the chat. So first of all, open that file that I shared with you in the chat, and now go into the group discussion. All right, now please put your bolt within 5, uh, 5, 4, 3, 2, 1. All right, so, for some reason, it's always problematic in Zoom that I have no way to see what was the. All right, so let's see. Okay, so previously, well, so now I'm inviting one of the group to. So now I'm inviting one of the group to share your thoughts with us. So if you are ready to share, please raise your hand. Please raise your hand. Okay, Rogelio, which group are you? You are faster.
Group red.
Okay, group red. Woohoo!
Yeah, we basically ruled out 3 and 4
Uh-huh.
and believe 1 and 2, at least most of us believe 1 and 2 are true.
Uh-huh.
So the answer, we put C.
Okay, so you put C. 1 and 2 are true. So okay, Xinan, I believe you are in blue, right?
Yeah, I'm in blue.
Okay, so Rogelio, stay online and I will keep you unmuted. So what do you think?
Our group thinks D, 3
Your group
is
thinks
correct.
D. Okay,
Yes,
so you think there are one more things. There are
yes,
one more
yes,
thing that is correct here.
yes.
Okay, what is that thing?
Uh, we think, should I tell you the one more thing now?
Yeah.
We think, we think the fourth option is not correct, but the other
fourth
3 is
option
correct.
is not correct.
Yes, the other 3 are correct.
Okay, so okay, so you think the fourth option is not correct, and what's the reason?
Because we think virtualization may use some techniques called context switching. The context switching can cause penalties because there are overheads. And when executing each programs in turn, there will be context switches, and it will not improve. It will slower the whole process. That is, when you execute, for example, when you execute 2 programs concurrently, the sum in time will be longer than if these 2 programs are executed one by one.
Okay, so Rogelio, do you agree with him now?
Yes, I agree. 4 is not correct.
Okay, then how about the third one?
Third one, we think this is based on my personal experience. When I was using Windows XP, for example, when I was young, I know a technique called that is to map some memory. That is to map some space in hard disk. For example, you can map some space in hard disk as a virtual memory, so as to
virtual
improve.
memory, right? That's memory virtualization, right?
Yes.
So with virtual memory, you don't need to worry about how many physical memory that you installed.
Yes. So the technique here is that you can use some disk space as some memory, although the speed will be slower, but you have more memory.
Okay, so Rogelio, are you convinced that the third is also correct?
Well, it depends on how you look at it. I mean, the third one, there's one reason why I think it's incorrect, and then one reason why it may be correct. I
So
think
why do you think it's incorrect? Let me see if I can address that for you.
Because it's saying that virtualization may allow a program to use more than installed memory. But in my mind, I see it as it creates this illusion that there's an
Yeah.
infinite memory, but it won't allow you to use more than the physically installed memory. At least not the OS will not allow you.
No, the OS would allow you to, well, the OS allow you to do that because we create the illusion. Right?
Okay. So
Right.
The OS will allow you to
Right.
use an infinite amount of memory.
Yeah, so one thing that I can tell you is that if you don't trust me, right, you can create, let's say, like a matrix multiplication program, right, in a Linux system. And it allocates more than the physical memory installed. And you use the program top to see how much memory has been used. And you will see how the memory usage surpasses the installed memory size.
Oh, wow.
Okay.
Okay.
Right. But the whole idea, okay, thanks both of you. So now this run, we believe Team Blue, because so sometimes, right, first come doesn't mean that you will get a score, but the Team Blue really give us the complete picture about why we want virtualization. So I will give Team Blue a score this time. So the reason why we want virtualization, first of all, it can help utilization and throughput of the underlying hardware because we allow concurrency, and if something is unused, we can utilize it, and allow the system to execute more programs because we have multiple programs running together in your machine. Even though your mobile phone right now, there are a lot of spyware running in the back end, even though you are not looking at them. Right. So one of the example is like, well, whenever you are talking, like your Facebook Messenger may be listening to what you are talking in the meantime. And then later on, surprisingly, you found that on your desktop, your Facebook would give you those like advertisement regarding commercials regarding to what you guys just talked with your friends. Right. So that happens a lot. Right. And like virtualization will allow the program. We just gave you examples that you don't need to worry about how much memory I install in the system, but I can still run it. The only thing that if you look at the second and the third point, the operating system actually make the software engineering industry true in a way that because you don't need to worry about the number of processors that you install in a machine, or you don't need to worry about the amount of physical memory you installed in your machine. So it makes program less machine independent. So it gives us the chance that you have the industry that we can just write our programs, compile the program on one machine, and the program will be used, will be able to run on another machine with the same library conditions, with the same operating system. No need to worry about the hardware. So the software industry will work. It's just because you have the operating system giving you such virtualization. However, as Team Blue just mentioned, because you have there's no free lunch, and the overhead of the operating system is that sometimes we have to context switch, we have to change the mode. So it turns out that it won't execute the latency, it won't improve the latency of executing a program. In fact, it will make your if saying that if you have a machine dedicated for this program, it will definitely be running faster without an operating system involved. However, because of the top three, the three benefits that we mentioned above, we still embrace the idea of operating system. And now the whole idea is that how we can make the fourth one as little as possible, right? So so now we know there are a few things. First of all, the operating system is providing the virtualization of your system, and this virtualization is called process, and it's actually the most important abstraction in modern operating system. So the idea of an operating system is that we provide a vehicle of virtualization. So every process that you see here, they own their own virtualized processor, virtualized memory, and virtualized I/O, and they access these facilities through an API. And for each process, this is for each running program, we call it a process. This is what we see. The process use the API, and they can manipulate the processor, the memory, the I/O. So that's the whole virtualization idea. And process is the most important abstraction in this way, is that it abstracts the whole underlying machine. And the whole underlying machine, as we said, is a von Neumann machine. So the von Neumann machine has a processor, has memory. So, and the program itself is just a static file, contains instructions and static data, as we show, as we shown you in the very early slides. And the process itself is a program in execution, or say a live program and a living program. And this program means that it's not only the instructions, but also where are we in a program, and what data has been changed since we start running the program. So you can say for the static part, like the instruction itself, they are just that program. But the states, the architectural states, as I said, where are we in the program, and where are the values of those variables and the data? They evolves over time. And a process as a virtualization, as an abstraction of a running program. In the operating system, it could be dynamically switched out back during anytime during the execution. So with the abstraction code process, right? This is what the operating system looks like. So an operating system is basically present an illusion of a virtual machine to each running program, and for each running program is called a process. And a process contains both programs and the architectural states of a virtualized von Neumann machine, like what's the register values in the processor, virtualized processor, what's the memory usage, and where are your data in the virtualized memory, and how can I what IO devices I can see, and how can I manipulate that. And each virtualized environment can access those architectural facilities through some sort of API. And this API right now in the operating system abstraction is called system calls. And how to dynamically map those virtualized resources into physical locations, that's about the policy or mechanisms provided by the operating system. So you have learned a lot of different terms in your operating system class in the undergrad, but without the picture of virtualization, it's hard to know why we need this. So this class is going to tell you why. We have this, right? So to provide an illusion of virtual machine, we have the abstraction of process to represent a running program. And the reason why we have system calls is because we virtualize those hardware resources. And for the operating system to get involved in manipulating this hardware resource, you need the system calls. And you learn a lot of policies, you learn a lot of mechanisms in changing processes or sharing the resources. That's all because you want to dynamically manipulate the virtualization resources. So this is the whole picture of the virtualization of operating system. So what happened when you run a program, right? So first of all, as we said, the program itself is just a persistent store. It's just in persistent storage, which contains your code and data in the very beginning. And then when you want to launch a program, right, the operating system will first create an abstraction, and this abstraction code process. And as we said, the process contains the whole von Neumann machine, and one big part of the von Neumann machine is the memory. So we will create the operating system will create a virtual memory space in a process. And after we create a virtual memory space in a process, you will load your code, you will load your data into the virtual memory space. And later on, when you execute your program, if you have a global variable or say dynamically allocated memory space from the virtual memory space, it will come from a heap, which is the section of the red part right after the static data section in your virtual memory space. And if you have a local variable, they will come from the end of your virtual memory space called stack. So this is how you grow how you use your memory space dynamically. And then so this, And then after you create a virtual memory space like this, you may have a lot of processes with their virtual memory space. The operating system would dynamically, well, no matter how you no matter how you do it, you probably learned like round robin, you probably learn FIFO, you probably learn a lot of different mechanisms, policies, right? No matter what you decided to do, the whole job right now is that when the operating system schedule the running program is all by the process based. We just see the process and we dynamically map each processor to execute each process at any time. So that's the illusion provided by process. So every process will seem to have a processor memory space exclusively to its own. So in this way, that explains why when we ran the demo previously, right? Every program consider that I own processor 4, and every program consider that I own that memory address can execute without intervening each other. They don't affect others' memory values is because we have this process abstraction, and within each virtualized world, everyone thinks that everyone is supposed to own the virtualized resource exclusively, regardless how the underlying operating system would remap your hardware to the physical locations. So that's the illusion provided by your process, right? So now, since you know that the process is a very important illusion, so I want to invite you to think together with me. If I want to track the process, then how many stuff in the following do I need to track? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I believe you guys have an answer in your mind, but in the last run of the game, I don't feel like some of you are familiar with how we do it. So now make sure that you open the file that I have been sent out through the group chat, and before you accept the invitation of going into the breakout room. So now all of you go to the group chat, open the file, the screenshot that I sent out, and now go into the group chat. We are going to finish this one in, we are aiming at finishing this one in 2 minutes. All right, once you're done with your discussion, please vote again within 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now, I believe all of you have been like finishing your voting. So let's see, right? So before the discussion, well, we only have 85% of you think it's C, it's E, but now every of you think it's the answer is E. So I want to invite one of the group sharing us with your discussion during the breakout room, and let's see why you guys reached the consensus. Okay, Josiah. So I saw you first. Which group are you?
Blue, group blue.
Blue. Okay, so Team Blue. What do you guys think?
Well, it needs to track the stack pointer so that when it returns, it can tell where it was on the stack, and the program counter to where it was in the instructions for the code. The process state, whether it was like running or blocked, like if it was waiting on IO, and then the register values for any CPU operations that were being performed. So
right. So basically everything. Right. So basically everything, right? So the answer is E, and I'm glad most of you get it, right? So So in addition to those, right, you also have to check a lot of things like, oh, okay, what's my process ID? What's my what's the process status? What's the IO status, and etc. Right. So actually, for each process, the operating system has a process control block for each process. And sometimes it could call test controlling block TCB, test struct, or switch frame. And the data structure in the operating system kernel would contain the information needed to manage a particular process. And it's the manifestation of a process in an operating system. So it's part of the kernel code. And how many of you have read the kernel of Linux before? If you have read the kernel of Linux before, raise your hand. Let me see how many of you read the kernel code of Linux before. 1, 2, 3. Okay, 4. Okay, 4 of you. And actually, how many of you were here? So put your hand down. How many of you were here watching the opening video for today? 1? Only 1? 2? How many of you watched the opening video for today's class? So if you pay attention to the opening video, right, the first part of the opening video is actually dumping the whole kernel source code. So if you pay attention, if you stare at the opening video, then you definitely at least you skim through the kernel code before. But right now, let me tell you where in Linux we maintain this structure. So if you have installed the Unix source code, you can find in the schedule.h, there will be a file. There will be part of the code. It maintains. It declares the struct of test struct, and the struct, the test struct, as we said, it's the PCB, the process control block for each process in Linux. And it contains several variables, but I highlighted a few ones that are especially important. Like it has the PID here. Oh, sorry, I have an offset for some reason. It has a PID here, try to give you the process ID. And it has the MM and active MM try to tell you the virtual memory pointers. And then it also have the struct, thread struct, to give you the low-level architectural states. So that's the test struct in Linux. So it does contain those information. And for each process, we maintain its state in a variable called state with runnable, not runnable, or stopped. Right. So that's the PCB. And with the pointer pointing to the MM struct, it tells you the current memory usage of the programmed in a way that it tells you where is the starting point of the heap and where's the end of the heap and where is the current stack pointer. So some of you might ask why we have the start of the heap at the end of the heap, but for the stack pointer only have one pointer. And the reason is because remember that the stack always starts at the very end of your virtual memory space. So if you have a virtual memory address space that's about like 64-bit, then it tells you that the last, the end of your stack is always 2 to the 64 minus 1. So you don't have to maintain the end of the stack because it grows from the end, and it only matters where your the starting point of your stack is in this struct. So that's why you only have one pointer for the stack. And for the stress struct, that's we mentioned where we keep the values, the register values for your processes. So if you look at that, right, those are, if you have ever learned x86 assembly language, these are consistent to the x86 register names like stack pointer, like ES, like DS, FS, GS. They are all they are all register names in x86. And IP, that's the instruction pointer or say program counter, specifically for the x86. So this is the evidence where your Linux does track all the stuff that a process needs to maintain, right? So these are the program counter. So the virtual, so if you think about that, well, this state changes all the time. Whenever you allocate, whenever you run an instruction, the program counter changes, right? So if it means that, well, the operating system has to know exactly where your program is cycle by cycle, right? So it will be really slow, right? If your operating, so whenever you move, your operating system has to update this data structure. That's really slow, right? So in fact, you don't want to consult this API to update your program counter anytime, right? So so this is too slow. So we don't want this to happen, right? So so it turns out that if you want this to execute faster, all you need is to have some kind of hardware support in modern processors. And this hardware support is that the hardware provide two different modes, the kernel mode and the user mode, at least to execute your program. And the hardware support is called restricted operations. So let's talk about this restricted operations. So the idea of restricted operation is that, well, most of the time, if it's not dangerous operations, for example, if I only want to do add to register values, usually, and as long as it's not a spatial register, for example, program counter, that doesn't hurt, then I should allow you to directly execute on the processor without operating system intervention, right? So it's like when you grow up, right? In the very beginning, when you are a child, your parents would always say that, well, no matter where you go, you have to tell me exactly where you go, what time you are going back. And later on, we trust that you are well behaved. Also, as we try to give you, we try to relax the restriction a little bit by just telling, well, at least telling me when you are back, right? And sometimes some parents doesn't even care about that, right? So same thing here is that, well, the process, the processor would allow, the operating system will allow the process to run without the intervention from the operating system. Most of the time, only when the program is trying to access some protected resource or the program really run into the trouble. So the second bullet here is that the operating system now only take care of protected resources. For example, memory is protected. For example, IO devices are protected. And when you say that I want to take a rest, okay, I will take care of that. Or you are running into some trouble and you don't know how to handle. For example, I have a divided by 0. I have an illegal memory access, right? When you run into this situation, that's the time when the operating system will intervene. So in this way, you can hear there are two different modes now, at least in operating system. The user mode, they are executing restricted operations in a way that you can your program will run some instructions that we define is safe for everyone to execute by themselves without affecting the security of the whole system. For example, arithmetic instruction, logical instructions. And the user mode is used by the user process. And we have the kernel mode. And when you are in kernel mode, you can, when your system is in, or say your program is in kernel mode, you can perform privileged instructions in a way that you can change the running process. You can take care of, you can access the protected resources, or you can access something to handle those situations. And the kernel mode is the kernel mode programs, the kernel mode instructions, the assembly is called the operating system kernel. So that's why every time when people tell you like, oh, operating system kernel, I have experience about the kernel. What the kernel is about is assembly of this kernel mode programs that help you to handle this protected resource, changing running process, and anything that the user program cannot handle. And if you really want this restricted operations to save most of your time in not entering the kernel mode, then it requires the architectural or hardware support. So some of the software engineers, they are pretty arrogant in a way that, well, they think we dominate the world, but actually a lot of success in a software is actually because you have the hardware support. Like this is a very good example. So right now, most of the processor will support at least 4 different modes. We code it like ring 0 to ring 3. So the processor will provide, will separate its own instructions into normal instruction and privileged instructions. So as I mentioned, if we just do arithmetic instructions like add, sub, multiplication, they are normal instructions. And for privileged instruction like HOLT, like CLTS, or some of the boot related instructions, or some instructions that you never use in your x86 assembly class, that's called privileged instructions. Then they can only be executed in the most privileged mode, for example, the ring 0. And usually the user process use normal instructions in the ring 3. And privileged instruction can only be used if the process is in ring 0 mode. So that's the distinction between the kernel mode and the user mode. And some of you might be asking me, oh, what is ring 1 and ring 2 used for? We will talk about this again in the very, very end of this quarter when we talk about virtualization. But now the only thing that you need to remember, at least we have the distinction of ring 0, the kernel mode, and the ring 3, the user mode. So to use privileged instruction, here is the process. So again, we said the user program, most of the time, we just do our own stuff. But whenever we need the operating system, right? So it's like you, right? So most of the time, well, you just do your own work, you just do your own study, and you don't worry about your parents most of the time during your age. And only when you like say, well, I'm running out of money, right? So you trigger a system call, which is actually a physical phone call, right, to your parents. Hey, I need money, right? So this is exactly like what happening in a program in a way that, well, most of the time I just do my own calculation. Whenever I need the operating system to help, I will call the API call system calls, right? So what happened in a system call is that we will, in the processor, it will have a trap instruction. And a trap instruction will raise an exception in a processor, which the processor that is running your program will notify that, oh, okay, this guy want help from the operating system. Then they will, like this one, right? The user program, then here I have a system call instruction. Then when I see that system call, right? The processor will save the exception PC, like, okay, like the system call, that's where you call the system for help. I will save the PC right now, and then the trap instruction itself would save the PC and jump to the corresponding operating system handler. For example, I need money, right? Then give me some money, right? So, and then the operating system kernel code, if you are allowed to trap into the operating system kernel, the operating system kernel, first of all, it will preserve the register value and the PC into the memory, so that later on we will be able to go back to the program, right? And then run the handler itself. And before return from the trap, we restore those register values from the memory. Right, so that's how that's the whole process of calling a system call and go into the operating system kernel in the privilege operations. So here I set system calls, right? But there are actually more things than system calls can make a program go into the kernel mode. And the reason why I only tell system calls here, because system call, if you look at the bullet, is raised by the application itself. However, the interrupt is raised by hardware, which is something out of your process's control. And exceptions is raised by the processor itself. So some of you said that like in Microsoft operating system, there's an interrupt 80. Yes, that's the system call, right? But it's called interrupt, but it used like in INT, but it's actually a system call. And exceptions, they are raised by the processor itself. It's mainly about like the processor detect that your program is running into some trouble, and the program itself won't know this, right? So that's the distinction between interrupts, among interrupts, system calls, and exceptions, in a way that interrupts, they are raised by the hardware, exceptions, they are raised by the processor, also hardware. Only the system call is triggered by the application itself. So that's why here I only put system calls as the example. But no matter how, those three will cause your program run into the kernel mode. So now you heard kernel a lot. I want to test. And a lot of you think that I am an expert in operating system because I get an A+ in operating system class. So right now, I want to test you by how much you know about the operating system kernel. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now you should have the question in your chat. And for this question, I do feel like we need a group discussion. It's not for you to practice. So this time, indeed, you need discussion. So go ahead, discuss within group now. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now, okay, so let's see, it's interesting. So this is what's after discussion. So we have seen B and E, they are both popular. And before discussion, as you can see, wow, it's really like a normal distribution. And surprisingly, after discussion, nobody think the answer is C. So let's see, like both groups, like let's see, like what your thoughts about this question. Please raise your hand, and if like I heard like in some group you have pretty good discussion, so why not bring up this to the whole classroom? Okay, so I have Emmanuel. So which group are you?
I'm part of group red.
Okay, what do you think?
So we did a little bit of a process elimination. It doesn't make sense for E because it can't be both always executing and should be executing as little as possible. That does not make sense to me because that's just contradiction.
Uh-huh.
We ruled out A because it is not a process. And so if A is not correct, then D is not correct. And so when we only were left with B or C, and the reason why we went with B is because it's more of a process manager. It creates and ends different processes. So that's why we went with B.
Okay. So anyone well, so let's say like what Xingyun, which group are you? What do you think?
Yeah, I'm from Team Blue.
Uh-huh.
In our team, most people think E is right, but we have a discussion about the option 3. So the answer of our group is between B and E. Let's talk about A first. We think the OS executes at a bunch of processes, not a single one. So A is wrong. And for option B, most of us think B is right. Because the OS is for the process winner. But in option 3, I think C is right because if OS take too much resources, our user program cannot run very efficiently. But some of our teammates think C is wrong, and we don't have enough time to discuss with that. So that's our answer.
Okay, stay online, both of you. Josiah, what do you think?
I was also in blue group. I was just pretty much going to echo most of what he just said, that it's always executing because it's providing things like context switching, and it's managing part of the processes. So if it's not executing, it can't perform those tasks.
Okay, so
I also chose E because I thought that it made sense that it should not get in the way.
Okay, so that's why I saw B and E, they are popular answers, right? So but all of you stay online a little bit, and then let me explain it. Right, so the first one, well, least amount of people chose it because you think it's not a process, and most of you learned it from the textbook reading, right? And here I give you an example why it shouldn't be a process. Because thinking about the process is a user program, and it could be context switch anytime. So saying that if your operating system kernel is context switch out, then who can bring it back? Nobody, all right? Because context switch it back also need to access the kernel. And if your kernel itself is a process, then nobody can bring it back. So this idea won't work, right? So that's the very basic idea why the kernel itself cannot be a process. B, is it always executing? So thinking about your processor, right? So that's why knowing the hardware is really important. The processor itself only has a program counter, meaning that anytime the processor can only run one program. So if you are in a system that only has one processor, which means that your computer can only execute the kernel, but not any other thing. So B cannot be true. So for the three of you who is currently online, do you agree with that?
Yeah.
Right, so B cannot be true, which is the most popular answer here, right? So now, right, you guys should know that B is also not true. So the only thing that is true is C here. And the operating system only get involved when necessary. And this necessary means system calls, hardware interrupts, exceptions. And the operating system kernel works on behalf of the requesting process. So the operating system, as I said, right, you only call it when you need it. Like most of the time, you don't feel like my parents are monitoring my life. I live by myself, but sometimes I still need help. So that's why I have the system call, or I have a smartphone calling them, right? So the operating system kernel, exactly like your parents, most of the time they don't intervene in your life, but whenever you need help, they would help you, right? So it works on behalf of the requesting process. So whenever you need something to help, then the operating system would work, kernel code would be part of your running program in a way that we trap into the operating system kernel code. So the operating system kernel code will be a function, like a function call, but a spatial function call called system call that your user process invoked. And the function code would execute using the same process ID, the same abstraction the requesting program is. So it's like a function call to a dynamic linking library. And the code itself would preserve the current architectural states, update the PCB. And as a result, you can imagine there are lots of overhead here in copying, preserving the registers, allocating the local variables for kernel code and etc. Right, so that's the operating system kernel code. And because they have this overhead, so it should execute as little as possible. Right, so most of you think like, well, I'm really good at operating system. I hope this question would give you an idea. Rethinking what you have learned in the past is that when you only know the what and how, you don't have the big picture of the why, then you are going to miss a lot of things regarding the operating system. So now I believe most of you would agree that the operating system itself kernel itself is not a process. It's not always running. It should execute as little as possible. Okay, Xingnan, question? Xing'an, question?
Yes, I have a question. We know that some network programs need to send packets into the network, for example, when using TCP or UDP. So if this option C is correct, does it mean that the user program that does the network operations should not execute it as more as possible?
So you raise a very good question. So yes, by default, because access network requires privileged instructions. So a network program will go into kernel mode frequently. And that's why sometimes you feel like when I run the server or the client program, whenever I'm doing network transactions, I have a lot of overhead. So and everything below TCP, they are in a kernel mode. But recently, because people have the idea of like user mode network, try to virtualize your network down to level 2, layer 2 of your network. So that's how people lower the overhead of data centers. But in the network programs, that applications you are running nowadays on the Linux, on Windows, every network, any traffic that you generate to the network or grab from the network, they involve the kernel mode. So they will be slow.
Okay, thank you.
All right. So yeah, so that's a very good question. So you know, like, okay, I want the kernel to be executed as little as possible, and because it's really slow, right? So so I think we are running out of time. And before you leave the classroom, there are a few things that I want to let you know. So we have 2 reading quizzes next week because we are going to discuss 4 papers next week. However, because I know a lot of you are going to read papers in the first time, so I split them into 2 because you need some time to figure out how to read the paper. And if you feel like, wow, the first 2 papers really freaking me out, don't be afraid, because later, because I sometimes feel like if no pain, no gain. So I really wanted to suffer for the first reading quizzes on reading papers, so that you will hear me, hear what I'm saying, hear what I'm teaching. Like the last reading, like the last pop-up quiz that I gave you, like I want you to know that, oh, I don't know what kernel is. Then you will listen to what I'm going to teach you in the rest of the quarter. So hopefully through this lecture, you will know that, well, there are still a lot of things that we need to know about the operating system. And through the process of reading papers, you will pay more attention to the next lecture, which I will parse a paper in the detail and teach you how to read the paper really quick. And I can tell you that in the past, one of my students, he read 2 days to read a paper, and now he only needs less than 2 hours in reading a paper. So I will teach you how this magic will happen. Other than that, enjoy the rest of the week, and I will see you again next week.